Okay, so what we want to have a look at this particular chapter is to have a look at the properties of random variables and combinations of random variables, okay? So if we start off initially just with a discrete random variable, what we're saying is that if we can have a linear function of that random variable, so if x is a random variable, then y equals ax plus b is also a random variable. That ties in a little bit with our methods. And let's consider what the mean and the standard deviation of such a random variable is. So our discrete random variable, we might be tossing a coin, and there's my probability of successes. So if we decide to turn our coin toss into a game, a gambling game, heaven forbid, where we might charge $5 to play and you'll get back $2.50 for every head that we toss up, okay? So obviously the probability of 0 heads is tail, 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 so it's 1/8, 1/8, 3/8, 3/8, 1/8. So there's my probability distribution, or the probabilities add to 1, so we know it's a distribution. So if W is my amount that I win, if I have 0 heads, I actually lose $5, okay? And the probability of that is 1/8. If I have 1 head, I lose $2.50, and the probability of that is 3/5. Similarly, if I get 2 heads, that will mean I'll come out square for a 3/8 probability. 3 wins gives me a win of $2.50, and I get a 1/8, yeah? So each of those outcomes is really negative 2.5x minus 5, all right? So that then ties in with our probability of winning more than 2. Well, it's obviously just the last outcome. I need to get 3 heads to win more than $2, so the probability of that happening is 1/8, all right? So what we're saying then really is, if y is some linear function of the distribution x, well then the probability that y is less than some y value, okay, can be rearranged to tell me what the equivalent x value is. So really, if y is equal to ax plus b, if I transpose that, x is equal to y minus b on a, which is what we're getting in here, okay? And so then we're just working out the probability for that corresponding x value, all right? Now maybe, what have we got? A continuous random variable, okay? Same principle. I've got a random variable here, where y is equal to a quarter of x between 0 and 2, and greater than 2 or less than 0 otherwise. If I want to find the probability that x is less than 1.5, well, I know that's the same as the integral between 0 and 1.5 of f of x dx, okay? So I might just take the quarter out the front, leave my x in there, integrate all of that, and I work out that the probability of getting between 1.5 and 2 is 9 on 32, all right? Now, if I've got some y is equal to 2x minus 1, what's the probability that y is less than 1.5? Well, really all I'm looking to do is work out a corresponding x value. So if y is less than 1.5, if I rearrange that, that's the equivalent of saying x is less than 5 on 4. So the equivalent integral is exactly the same integral, but between 0 and 5 on 4. Okay, and then if I work out that, I'm going to get 25 over 128. All right, so it's just a case of keeping track of which variable we're referencing, okay? And for our linear and continuous distributions, if we're manipulating the distribution by some linear function, well, my probabilities don't change. What about the mean? Well, from our methods talk, we know that if I've got some expected value, if y is equal to some ax plus b, the expected value of y is the expected value of ax plus b, which is just a times e of x plus b. So that's the impact it has on the expected value. Okay, if I increase every value by a, well then the average, the mean is going to increase. And then if I add a value, well obviously that's going to affect the mean as well. The distribution is a bit different, it's the variance. All right, the variance of y, or the variance of some ax plus b, we know is a squared times the variance of x. Okay, so that applies through my distributions. So again, If x is a continuous random variable with mean mu equal to 10 and variance sigma squared is 2, well, the expected value of 3x plus 1 is 3 times e of x plus 1, which is just 31. The variance of 1 minus 2x is negative 2 squared, the a value, times the variance of x, which is just 4 times 2, which is 8. So hopefully there's not too much new there. All right. What if we're going to add two random variables together? Okay. What happens there? So what if we have a linear combination of two random variables? All right. So variable x, variable y represent two different random distributions. The expected value of ax plus by is just a times the expected value of x plus b times the expected value of y. In other words, those expected values are in fact independent of each other. Similarly for the variance, if I've got two processes going, what's the variance of the whole processes together? Well, it's a squared times the variance of x plus b squared times the variance of y. Again, the variances are independent of each other, and we just add those together. So that comes into play if we have examples like this where we have a manufacturing process. Maybe it's in two stages. The first stage is distributed, takes x hours. It's a continuous random variable with mean mu equal to 10 and a standard deviation sigma equal to 2. The second stage, distributed in terms of y hours, has a mean of 4 and a standard deviation of 1. Okay, so if I want to complete both of those processes, what is the expected value? What is the expected time it takes to complete? And what is the standard deviation? Well, expected value of x plus y is just the individual expected values, which is 10 plus 4, which is 14 hours. The variance of x plus y is the variance of x plus the variance of y, which is 16 plus 1, which is 17. So the standard deviation of processes x plus y is equal to the square root of 17 hours.